they're kind of anomalies on the land. Landforms that are made by wind are generally these gigantic sand dunes or loess, and then landforms made by ice are glaciers and things like that. So they're usually in very extreme environments, and yeah, and for some reason in my head I grouped them together, so I'm going to lecture on them together. All right, I have a couple quotes for you. A Gandhi quote: "You must not lose faith in humanity. Humanity is like an ocean. If a few drops of the ocean are dirty, the ocean does not become dirty." I thought that was a good quote considering our current situation where we feel isolated and alone and maybe are losing a little bit of faith. And then Bruce Springsteen: "Like a river that don't know where it's flowing. I took a wrong turn and I kept just kept going." So there you go. Two quotes for you. All right, so our landforms that are made by wind. First, you have to have the transportation of the particles. And so when we're transporting particles, when we're transporting mostly sand, but it can be dust or pebbles or small rocks. Depending on how strong the wind is, you're going to get you're going to get more or less particles that are moved. And I don't know if you notice that it's windier right now. It's windier this week, and it will be windier through spring. It tends to be windy in spring and in fall. There's a physical geography reason for that. And once we finish landforms created by wind and landforms created by ice, and once we talk about soil and biogeography, then we're going to get into the climate. And when we talk about the climate, then big part of that is wind. And I know you're like, oh, yay, I can't wait till we talk about air moving sideways. But don't worry, it's very interesting. Okay, so it's very windy right now, and there's a reason for that. And so stay tuned for when we talk about climate later. All right, so when we talk about particle transport by wind or water, we're talking about saltation. So saltation is our particle transport by wind or water. Surface creep is the movement of loose particles that are just like creeping along right here. There's particulates and particles that get pushed up into, if you have really strong wind especially, they get pushed up into the air. And if you don't have a whole lot of barriers like trees or something like that, then you can have these particles that are moving higher up in elevation. But our surface creep, those are the little things that just come right, like loose pieces of granular sand or whatever that get moved along down here. Just imagine, I don't know if you've ever been to the beach on a windy day and sand kind of like blows across your feet. That's surface creep. And so one thing I know you probably already know from this picture, but when we're talking about landforms that are made by wind and we're talking about sand dunes, we're probably talking about pretty dry places. We're probably talking about a desert, because one of the things that allows for the movement of sand and pebbles and things like that by wind is very strong wind, which is something that we see in the desert, and not a whole lot of barriers. So you can have this accumulation of this finely ground. Remember, this sand here would have once upon a time been a much larger rock. So the ability for that to be eroded down and then transported by wind and piled up, that means that there's not a whole lot of other things like trees or forests inhibiting the movement of that sand. Okay, so when we talk about, again, the movement of particles by wind, deflation, that's the lifting and transport of loose particles of soil or regolith. And if you remember what regolith is that pile of eroded rock that's underneath soil. And we haven't talked about soil. We'll talk about soil in our next lecture. Yay, I love soil. But soil is, I know you have a picture of what soil is in your head. So deflation, that's our lifting and transport in turbulent suspension by wind of loose particles of soil or regolith. Desert pavement, that's when so much has been moved away, when you have so much deflation that's happened. You've had particles of sand and pebbles that have been transported and lifted away by the wind, that you actually have this like hard, compact, all that's left is the sand that's like compacted into the ground, if that makes sense. I'm trying to think of an example of where something like that would be, but if you can imagine, instead of walking along loose sand, like on a beach, you're walking along what feels like very compacted. You're not gonna be able to like dig into it and dig a sandcastle in desert pavement. I mean, just look at the word pavement, right? Okay, transportation by wind, like I said before, depends on two major things. So, one is wind, and we haven't talked about climate yet, but wind, the advectional sideways movement of air, happens because air mass changes in the world. So, when you have warm air, air has mass. I know I've said that in class before, even though we walk through it, we don't think about it as having mass. But when it lifts, when it heats and it lifts, that creates an empty space. So, other air rushes in to fill that space. And that other air that is rushing in to fill the space of the displaced, um, my dog is snoring. Can you hear my dog snoring? It's distracting. Um, when air is moving sideways to fill in that now empty space that's created by the warm air that's lifted, well, we call that wind. And so, if you're in a place that doesn't have a whole lot inhibiting the movement of air and wind, like I said, if you don't have a lot of mountains or trees or something that's going to stop the accumulation of particles as that air is moving to the side, well, that's when you're going to get a whole lot of wind and particles in what we call a dust storm or a sandstorm. Now, you see a lot of sandstorms in Asia, in East Asia, in Mongolia, in China. They can reach all the way to Japan and Korea sometimes. In fact, particulates in the air can get caught up in the transportation of air around the Pacific Ocean, and you can see remnants of gigantic dust storms in San Francisco and along the California coast. Dust storms that start in China or in Mongolia. And if you think about China and Mongolia, we're talking about Asia, we're talking about a gigantic landmass. And in Mongolia and in northern China, you have the Gobi Desert, a cold desert. It's very dry, so you're not going to see a whole lot of trees, a whole lot of large um, natural structures that are going to obstruct the movement of this and the transport of all of these particles. And so what you're going to get is just giant accumulations of dust and particles over hundreds, sometimes thousands of miles. So yeah. All right, so what is a sand dune? A sand dune is what we call an aeolian landform. Aeolian just means a landform that's created by wind. So a sand dune is permanent. It's not just something that comes like up in a day and then blows away the next day. It's a permanent landform, or as permanent as landforms are, and it's a hill a hill or ridge of loose, well-sorted sand. Now, the top of this landform of this sand dune is going to be somewhat loose, but there's going to be this can be a very, very large, almost like a little hill. Some sand dunes can be very high, or they can be almost 1,000 feet. So when we're looking at sand dunes, the top of it might be loose sand that still moves around and is, you're standing right here and you might get like pummeled with sand in your face. But the weight of all of this loose sand is going to lead to a really, really dense, compact, kind of solid mass of sand right here. So our sand dune forms when you have easily weatherable types of rocks. So like sandstone, for example. I know that I've held up sandstone for you all in class. Sandstone, did I say that? I've held up sandstone for you all in class, and I know that you can just look outside in Santa Barbara and see sandstone, but it crumbles pretty easily. So you take sandstone in a dry climate. There's not a whole lot of water, keeping those particles together. You get some wind, and boom, you've got eroded material that is being moved by the wind, and it is going to accumulate and start to pile and pile and pile, and pretty soon you're going to have this large landform that we call a sand dune. Not pretty soon, but pretty soon in terms of geologic time. So there's two major parts of our landform. We've got our slip face. That's our leeward face over here. So if you remember me talking about mountains and how air moves over mountains, you have the windward side of a mountain. That's the side that's getting hit with the wind. If you remember on like an island or when we're talking about the Sierra Nevada or the Andes, the windward side of a mountain, that's the side that's going to get a whole lot of water. That's the side where you're going to see orographic lifting. Air is going to condense. It's going to rain. That's not necessarily going to happen in this situation, but just so you can imagine what this would look like if it was a mountain. And then the leeward side, if you remember on mountains, tend to be dry. And so that happens because you're getting the air. So air goes up in elevation, it condenses, it rains, and then it comes back down. Once it hits the top of that peak, gravity pulls it back down. Now you're getting drier air. That's what's happening in mountains. But with this, the windward is the part that is accumulating, that is collecting sand. And the leeward, that's going to be the very steep side. If you've ever gone and slid down sand dunes anywhere, this would be the funner side to slide down. I used to do that with my dog back in the day. So the windward face is also called the angle of repose. That's the side that is accumulating and getting a whole lot of sand, a whole lot more sand. And then the slip face, the leeward side, that's going to be the steeper side. So the wind is kind of like going this way. And maybe it's like sprinkling some sand down here, but this is where the sand is accumulating. Okay, so when we have a great desert landscape, like through the Sahara right here, we call that erg. So erg is a great desert landscape. That's where you don't just have like a little orographic desert or like a little high elevation desert. These are our true desert regions. And when we go into climate, after we talk about biogeography, then we're going to really understand what that means, the true deserts. But that's something that I pointed out to you on the world map a couple of times, that we have this belt of deserts through the world at 20 to 40 degrees north and south of the equator. And that's where you get like our really massive deserts like the Kalahari, like the Sahara, like the Victorian Desert in Australia. So reg, that's our pebble landscape. It's semi-impermeable. So permeable is something that you can pass through, right? So semi-impermeable means that you could pass through it, but it's going to be pretty hard. The Sahara was once a much wetter place. At the end of the Pleistocene, and I'm going to show you pictures of what North America and Europe would have looked like at the end of the Pleistocene, but you essentially had an ice sheet that came all the way down through Europe. If you imagine this is the Mediterranean, Italy's going to be up here. I mean, it's not right there, but it's further up here. So if just north of North Africa was a gigantic ice sheet, an ice sheet is a collection of glaciers, and that ice sheet would have been, with a glacier, there's a zone of accumulation, something that it basically is like building up more snow, and then there's the zone of ablation, the part that's losing, basically the snow is melting. So at the bottom of Europe, you would have had this melting snow that would have come and created a very different landscape here. It would have been much cooler. There would have been a lot more water. Besides the Nile, there are ancient riverbeds all through the Sahara as a result of that little mini ice age we had. Okay, so our sand dunes, we have a couple different types of sand dunes I'm going to show you pictures of. I will just go into those. So our Aeolian landform, our first one is our Barchan. Our Barchan, see back here. And our Barchan is created when you have wind that's flowing in one direction. Now you're going to have to have something that allows for this sand to start to collect. So it could be like a larger rock. It could be you're going to have basically a condensation nuclei. That's something that we talk about in clouds later. So it's not condensation, but you have to have some sort of nuclei, some sort of like beginning, starting point where this sand starts to collect and pile around. So when you have wind moving in one direction, notice how it creates this like nice little crescent. That crescent where the wind is hitting, it's carrying all of this material, these pebbles and sand and stuff like that, and it's really piling up right here, and then it kind of whips around, and then the wind continues moving. So you get this nice crescent. That's what a Barchin sand dune is. Our transverse sand dunes, that's where you have a whole lot of sand, no vegetation. And you might think, I thought these were happening in deserts, so there's never any vegetation. There's vegetation in deserts. But the transverse has to be no vegetation. You have one single dominant wind, and you have these sand dunes that form at right angles. So you're going to have one single dominant wind, you're not going to have any vegetation, and it's going to create these transverse sand dunes. If you remember the transverse ranges here in California, those are the ones that go against the grain. We've got the Sierra Nevada going north and south, the coastal um, mountains going north and south, and then we have the transverse ranges. That's the range that basically, if you if you look at a map of California from when you're going from Santa Barbara to LA, we think we're going south, but we're actually going mostly east, and we're traveling along the transverse ranges. So we have a transverse, it's transversing kind of, it's going across. And that's what's happening with our our sand dune as well. Our star, pyramid-like, formed with wind coming in several different directions. So we've got this nice, unlike the Barchin over here, which is this like pretty simple crescent, we've got, wind coming in multiple different directions and piling up. In these sand dunes, this is like, one of the sand dunes that we're going to see in Death Valley or something like that. Just these huge accumulations of sand that are a result from the wind coming in several different directions. And then we have our parabolic. That's what we're going to see along the coastline. Like if you've ever been to Pismo Beach, there's ice plant along Pismo Beach. And so you've got a whole lot of sand, but you also maybe have a moist wind coming off of the ocean that allows for some plant life. And you're going to see an accumulation of sand around that plant life. Basically, in this scenario, the plant life becomes the condensation nuclei. Now, I'm using that term. That's a term that's used for clouds, but just to give you an idea of there's some sort of nuclei, something that like had to start this pile. Okay, oops. Yeah, parabolic we talked about. And then longitudinal, this is essentially desert pavement. This is what desert pavement would look like, what I was trying to describe earlier, where you have like hard, compacted sand. You don't have a whole lot of loose particles moving around here. So deserts with little sand, you've got one prevailing wind going in one direction, and you have these nice long parallel ridges, and they're going to be pretty hard. Now, low S, I said that word earlier, and you've probably heard of low S before. But that's where you have surface that you have a wind that's transporting sand and pebbles and stuff like that, but it's also transporting silt. And if you remember back to when we talked about rivers and what rivers are transporting, one of the things, if you remember, they're transporting is silt. So you've got a little bit of biomass in here, or maybe not biomass, but a mineral content that is going to be more conducive to growing plants and growing a variety of plants. Low S, you get a loosely compacted kind of yellowish gray deposit of silt and sand, and it can lead to a differently fertile type of soil. So there's a low S plateau, for example, in Mongolia, and then we have low S distribution here. And I posted this on your canvas. This is and please watch it. This is a National Geographic about sand dunes and how sand dunes can actually like create these incredible sounds with the wind passing through them, passing through like the hard or compact core of the sand dune. So please go and watch that. Okay, I know that was kind of quick, but let's move on to glaciers, our other landform that we're looking at that I said is kind of an anomaly. Glaciers and sand dunes. And glaciers, like sand dunes, are landforms that we see in extreme environments. So with our sand dunes, we tend to see them in extreme heat, or really it's extreme dry. That's where we're going to see sand dunes. It doesn't have to be very hot because the Gobi Desert is a cold desert. You see sand dunes and you see low S there. And then glaciers, once again, it doesn't have to be, glaciers can be in a pretty dry place, but it has to be very, very cold, obviously. So glaciers, a lot of people think that this is a glacier. This is not so much a glacier. Sorry. This is not so much a glacier as it is an iceberg. And if we were in class, I'd tell you a joke about icebergs, but I won't. I'll save that. A glacier is actually much, much larger than an iceberg. And if you can imagine, an iceberg is pretty big. I mean, an iceberg took down the Titanic, right? So if an iceberg is just a piece of a glacier and it was big enough to take down the Titanic, imagine how big glaciers are. So what a glacier is it's a frozen river. And I called it a landform before, but the glacier itself is a frozen river and it creates other landforms. So it creates both erosional landforms and depositional landforms. And if you remember those from before your midterm, erosional landforms are created when you basically remove material, and depositional landforms are created when you deposit that material, when you then take that removed material and you move it somewhere else and you pile it up somewhere. So with glaciers, we want to look at what glaciers are, what different types of glaciers there are, why glaciers are really important, and we want to look at the landforms that they create. So I love glaciers. Glaciers are these gigantic, enormous, incredible frozen rivers that carve out they have so much effect on the landscape. If you look at Canada, for example, Canada has 60% of the world's lakes. And the reason it has so many of the world's lakes is because once upon a time it was covered in an ice sheet. An ice sheet is essentially a collection of glaciers. And those glaciers carved out these gigantic holes in Canada and conveniently filled them with water, leading to all of these incredible lakes. But I think what I love about glaciers, besides that they are just like majestically, quietly, I mean, that's probably not that quiet, but majestically and quietly beautiful, is that they're also they're also so unassuming. Like you look at them, and because they move at a quote unquote glacial pace, meaning they move very, very slowly, um, we think of them as kind of being permanent and in place, but actually they're constantly moving. They're constantly accumulating and also losing. So, like one end, they're going to be accumulating, another end, they're going to be melting and losing material. And they create this. They have this huge impact on us, and we don't even think about it because they're so slowly, gradually moving around us. They're kind of like the Ents of Lord of the Rings. If anybody out there is nerdy like me and remembers what the Ents are, the Ents are like the big tree people. Kind of glaciers have always reminded me of those Ents. Okay, so our cryosphere. When we talk about the cryosphere, we're talking about the portion of the hydrosphere. And remember, the hydrosphere is the water sphere, in which water is stored as ice. So if you remember, we talked about how the Earth is covered in 70% water, but most of that water is, say it in your head, ocean water, seawater, right? Salt water. 2% of it is kept in ice, and that's what we refer to as the cryosphere. So when we look at our fresh water, one of the reasons that glaciers are so important is because that's where most of our fresh water is. So most of our fresh water is being stored right now in glaciers, or the sisters of glaciers. And I'll explain what I mean by the sisters of glaciers in just a minute. So a glacier is any large natural accumulation of land ice, and it is moving. Glaciers move. They don't just move because they're melting and they are accumulating. So they're building up snow on one end and they're melting on another end. but they're also very slowly moving. So imagine that we have this definition of glacier right here, but I always explain glaciers as a frozen river because a river is gigantic, and imagine it frozen. Imagine the weight that that would have on the landscape, for one. And the bottom of that glacier, the very bottom of the glacier, the part that's touching the actual earth, that's going to be heated by geothermal heating of the earth. So the earth has its own heat that it's radiating out, and that glacier is snug right up, packed right up against that geothermal heat. And so what you have is this little slip and slide that happens at the bottom of glaciers. What you have is this like little bit of melted ice at the bottom of this gigantic heavy thing. Sorry, not melted. Yeah, I mean melted ice, um, or just liquid water at the bottom of this gigantic heavy frozen river. And so what happens is it's just like slowly sliding along because it's got a little slip and slide action underneath it. What you guys can't see is I'm doing a whole demonstration with my hands. And I don't know to whose benefit I'm doing that for. If not my dog, who is asleep, then I guess just me. All right, so what we're looking at right here is, remember, not a glacier, that's an iceberg. And this is the end of a glacier. We're going to talk about what kind of glacier that is. These are two different types of glaciers right here. So we've got an outlet glacier. Why do I have that right there? Oh, that's why. Sorry, I thought that was a repeated slide. So an ice cap, you've probably heard that term before, the polar ice caps. Maybe you've heard me say ice cap. I'm sure you guys have heard of an ice cap before, but that's a continuous mass. So a continuous mass, a glacial mass that covers mountaintops. It's usually dome shaped, which is a little bit different than the kind of river shape that I've been describing for you. So an ice cap, that's a type of glacier, but the difference is that it covers mountaintops, right? Like it's just covering the mountaintop, and it tends to be dome shaped. An ice field is when you have interconnected valley glaciers. So some glaciers accumulate in valleys. You have, and I mean, they create valleys. But if you imagine, I'm going to show you different pictures of glaciers, but if you imagine like a U-shaped valley that is created from a glacier, and you have a whole bunch of glaciers filling these U-shaped valleys, they're all interconnected, kind of spining through a mountain chain or something like that. That's what we call an ice field. And this is a nice ice cap in Iceland. So see how that's like, it's coming, this is the glacier kind of like coming down to the terminus, down probably lower elevation, but see how it's capping, and it's kind of a nice little dome at the top of these mountains. An ice sheet is a large, thick plate of glacial ice. It moves outward in all directions, as opposed to an ice shelf, which is a plate of floating glacial ice. So floating glacial ice versus an ice sheet. I'm going to show you the difference in just a minute, but what we're looking at is covering a landmass, possibly covering landmass plus floating on water. So a big difference between an ice sheet and an ice cap is size. An ice cap is not nearly as big as an ice sheet. So if you imagine, we're talking about ice sheets up here. We were talking about ice sheets right here, and we were talking about ice caps here. So an ice cap is kind of a smaller version of an ice sheet. That makes sense? And then an ice shelf, part of that is going to be floating. All right, or most of it's going to be floating. This is Greenland. And this is Iceland. Notice that Greenland is covered in ice and Iceland is covered in green. That was intentional by the Vikings. Apparently, they named this Greenland because they wanted people to be tricked and to go here to this icy, cold tundra place instead of going to Iceland, which is actually a pretty green, pretty amazing place. So the Vikings from over here intentionally kind of like misled people and called this Greenland. They're like, it's so green and nice over there, you should go there and not come here. because this is where we're going to be and it's much better. Okay, so we have the ice sheet that's over Greenland. And the Greenland ice sheet is a big deal because it is very, very large. And as it retreats, we're going to see, so retreating, meaning that it gets smaller and smaller. That's going to have some pretty detrimental effects. One is sea level rise, right? If we have a whole lot of our fresh water locked in ice and we allow that to melt and become salt water essentially, well, one, we're losing access to a lot of our fresh water, and two, this does more for us than just provide water. It also reflects the sun. When we talk about climate later, towards the end of the semester, it reflects the sun, which is one of the ways that our temperature stays balanced here on Earth, is the albedo of ice means that about 95% of the sun's energy gets reflected back instead of getting absorbed and turning into heat here. And it also, keeps you have this cool air that's coming off of these ice sheets or off of this ice sheet, and so that cool air is going to spread and it's going to keep other places cool as well. And so if we lose that, then we're essentially losing a whole lot when it comes to the balance of our climate. And I don't want to get too much into that because I will explain that in greater detail. It'll make more sense when we talk about climate later. Antarctica is another one of our ice sheets, and this is Antarctica. Antarctica is a continent. It's unlike Greenland, which is an island, or sometimes people think that Antarctica is basically just ice. The Arctic is ice. The Arctic is where we're going to see ice shelves as opposed to the Antarctic, which is where we see ice sheets. And the Arctic is, or sorry, damn it, the Antarctic is a interesting place. That it's the continent in the world that is the highest, the driest, and the coldest. So some trivia for you: Antarctica is the highest, driest, and coldest continents in the world, meaning that it's actually very high in elevation. It's very mountainous. It's very dry. And a lot of people are like, but it's covered in ice. Yeah, but the air is dry. It's a desert. And it is very cold. That one was probably not so much a surprise to you. When we talk about Antarctica, here is the South Pole. That's the South Pole. Very few people have ever been there. Maybe you've heard of cruises that go to Antarctica, or there's actually a marathon that people run in Antarctica. That's West Antarctica. So the part, if you know anybody or if you've ever heard of anybody going to Antarctica, unless they were like a serious researcher, very, very few people actually get to go to the South Pole. Most people, if they've been to Antarctica, go right in here to this western part of Antarctica. And so if we look at the continent of Antarctica and see how it is covered in an ice sheet, and we're looking at the western part, this is called the Wilkins. I think I had that earlier on a slide. Yeah, the Wilkins ice shelf. That is covering Antarctica, and so it's covering part of the continent, and it's going to, depending on the time of year, if it's winter, it's going to cover, it's going to basically go over this water. So you're going to have the floating part of that ice over water all through here. That if it's hard to talk about polar bears because polar bears don't live in Antarctica, but in places like Antarctica or in the Arctic, you have this permanent ice and you have this temporary ice, this seasonal ice that seasonal ice usually spreads out over water as opposed to the ice that remains on a continent. And that seasonal ice is what's really important for different animals that are surviving in this landscape. So polar bears, and again, polar bears do not live in Antarctica. They live in the northern hemisphere. But just imagine that you have this, the reason that they're endangered right now is because you have this temporary seasonal ice that floats out over this water right here. And what happens is there's cracks and there's holes in that seasonal ice, and the polar bears wait, and then a seal. So seals can hold their breath for a very long time, but they have to like pop their head back up, and they pop their head up through the seasonal ice to breathe. And the polar bear is waiting there, and it's like roar, right? And it attacks the seal, and that's how it gets its food. But every year, as the climate gets warmer and warmer, the seasonal ice gets less and less and less. And as it gets less and less, that's less hunting time, that's less space for the polar bears. That's one of the reasons that they are in such trouble right now. And we'll come back to that when we talk about the climate as well. So, Antarctica here, and then Antarctica covered in its ice sheet. And then here's the ice shelf that makes its way back. Remember, ice shelf, ice sheet. So, Antarctica here with its ice sheet, and then the ice shelf comes out over the peninsula. um, Here's an ice cap once again, the dome-like kind of joined glacier that we call an ice cap. This is Glacier Bay in Alaska. Glacier Bay in Alaska, if anybody has been here, I've been here, you like can only get in here on a boat and you see all of these glaciers, what are called tidewater glaciers. It's mostly what you're going to see right in here. But if you look at this map, what we're looking at is where the glaciers were, like in 1860, for example. So in 1860, these glaciers that are here, came all the way out to this red line. And in 1845, they were here. In 1794, they were here. Just to give you an idea of how glaciers have been retreating for quite a long time now. And again, that's really important because a whole lot of our fresh water is kept in those glaciers, for one. So we're losing fresh water as we need fresh water more and more. And we're losing the albedo. We're losing the reflective capability of this. And again, we'll get to that later when we talk about climate. So to give you an idea of our global retreat of glaciers, looking from 1980, when I was just a tot, to 10 years ago, and look at the retreat, just the general retreat. And if you have any question of why we're seeing glaciers retreat, it's because the climate is changing and heating up. And again, we will talk all about climate change in lectures when we finish soil and biogeography. So glacial effects on sea level, besides that we are going to lose a lot of our fresh water, where our fresh water is stored, we're also going to, if you melt a bunch of glaciers, it's going to increase the water supply to the world's oceans. So not the fresh water supply, but the water supply to the world's oceans. And that means, like I said, that we're going to have less reflective capabilities, but we're also going to have more water in the ocean, which means that if we live along the coast, which we do, that means that we're going to have less coastline. So when we talk about climate change leading to sea level rising, this is where it's happening. It's because of all of the fresh water that's going to melt into the ocean and cause sea level rise. There was a terrible movie about sea level rise in like a post-apocalyptic world called Waterworld. It came out in the 90s. It was just an awful movie. Anyway, so, and I was an extra in that movie. So isostatic rebound, that's another thing that happens when we see glaciers melt and retreat, and a place that maybe used to have a glacier doesn't have glaciers anymore. So here, the principles of isostatic equilibrium. When you have something that's very heavy and frozen, it's going to squish down the crust. I know that that's not the most technical term to use, but just imagine it's squishing, right? It's pushing this down. Now, when you have this big heavy thing that's removed, now this lifts up, right? The landmass lifts up. It's the same thing when we talked earlier in the semester about exfoliation, that type of mechanical weathering that happens where you have a glacier or you have an ice sheet that is moving along slowly, like in the Yosemite Valley, for example. That's a valley that's created from a glacier. And so when that glacier went away, not only did that glacier like leave this gigantic valley, but that heavy, gigantic heavy weight now being gone meant that this uplifted. And so you're going to have now a higher elevation of this landmass, but also it's going to exfoliate. You're going to see kind of like, I explained this in class. I don't know if you remember. It's hard to explain without you seeing my hands signals that I, again, am doing for really nobody in particular. But what happens is like the little pieces on top here are going to break away when you have exfoliation, when you have the removal of a glacier. Um, and yeah, so isostatic equilibrium. This is what happens where you, if you can see that you have raised landmass, you have raised elevation as a result of isostatic rebound. And then thermal expansion. When things get warmer, they expand. That's why bridges are built with little grates in them. So like a bridge is never just a solid piece of cement or material, because when it gets warm outside, that bridge is going to expand. And if it doesn't have room to expand, it's going to break apart. And when it gets cold, it's going to, you know, contract. And once again, if it doesn't have the room to contract, it's going to break apart. So when we see the end of our glaciers, when we look at glaciers melting and retreating, not only do we see the isostatic rebound, but we also see thermal expansion. And that can be responsible for sea level rise as well. Okay. Ooh, the Gulf of Bothnia. So here we have Sweden, and we have Finland and Norway over here. This is a place where we're going to see plenty of glaciers for one, but also glacial valleys that have inlets that go out into the sea that we call fjords. I'm going to show you a picture of some of those. We talked about that when we talked about rivers as well. So because this is the Scandinavian Peninsula is a place that's dominated by glaciers and glacial valleys and fjords and lakes that were created by glaciers and all kinds of stuff, you also see once again an uplift from what we're talking about over here, the isostatic rebound, as a result of losing just the weight, literally the weight of the ice across this peninsula. Okay, so glacial melt, not surprisingly, can create gigantic volumes of water, large volumes of water, and a whole lot of countries like Sweden or Norway or Switzerland or somewhere like that, where you have high elevation, you have mountains, you have pretty cold temperatures, you're going to have a whole lot of fresh water as a result. Now, you can use that fresh water for, obviously, for water, which we all need, but it's also a source of energy, and it's a major source of energy. Now, if we look at climate change, and we look at how temperature is going to rise, and we're going to see the melting of more and more glaciers, that is going to be a problem for places like the Scandinavian Peninsula, for places like Sweden, not sorry, this is Sweden, Switzerland, for places like India, India, the north eastern part of India is the Himalayas, basically. And so India gets a lot of its water from the glaciers and the ice, the snowpack that's along the Himalayas. So what's going to happen when our temperature rises is those glaciers and that snowpack is going to melt and melt more increasingly. You're going to see flooding. And with that flooding, all the problems that we've talked about earlier with flooding. But then eventually it's going to all melt and there'll be no more water. So for places like Sweden with 10 million people, that's going to be a problem. Imagine what that's going to be for India with 1,200,000,000 people, when essentially their main source of fresh water literally dries up. So our glaciers are very important to us. And that's why it's very important to study glaciers. They tell us a whole lot about how global temperature is changing just from their melting, but also from ice cores. If we look at, it takes a long time for a glacier to accumulate. So if we take ice cores deep basically into glaciers, we can analyze those ice cores and look at gases that would have been in the atmosphere when that part of the glacier was made, if that makes sense. Um, so it can tell us about changes in maybe how much carbon we have in our atmosphere now as opposed to 100 years ago, 200 years ago. Um, yeah, so glaciers can tell us a whole lot. All right, it's no big surprise that glaciers occur where snow build up in winter. So you have basically long, cold winters, and you're going to have more snow build up than snow melt in summer. That doesn't mean you're not going to have a summer. Places like Sweden, places like Norway have nice summers, but it means that you're going to have a more intense winter that's going to allow for that snow buildup and not allow, and a summer that's not going to allow for it to completely melt. Um, when snow builds up, you have an increase in pressure. That creates something we call granular firn snow. I'm going to show you the definition of that in just a minute. And so that granular firn snow, that's the kind of loose snow that's going to be on top. Inside this glacier, so underneath, and you can see like a hint of the blue. If you've ever been to a place that has a glacier, maybe somebody warned you not to ever touch the blue ice. And if we were in class, I would say, do you know why? And hopefully somebody would say, because it'll burn you. Because there's so much pressure on that glacial ice. It's so compacted that it is so freaking freezing cold that it will literally burn you, like dry ice would burn you. It's not dry ice, but same kind of idea. So that's our crystalline ice, that dense crystalline ice that's going to be deep in the glacier. And the kind of looser snow that's on top of the glacier, that's our firn snow. Ooh, look, here's Canada. So remember how I've said that Canada is 60% of the world's freshwater lakes? I've said that once upon a time Canada was covered basically in a big ice sheet. Well, look, here it is. And when that ice sheet retreated, just imagine it digging out, basically carving up the landscape of Canada and filling up the landscape with a whole lot of fresh water, leading to a country in the world with 60% of the world's freshwater lakes, just one country. Now, Canada, if you took economic geography from me or if you took world regional geography from me, I would talk about what Canada's future is going to look like. Because Canada right now, so chill, right? Like, so nobody locks their doors. Everybody's got weed. Uh, I don't know, pharmaceuticals, healthcare, all that good stuff. They've got Justin Trudeau as their leader. But what is going to happen when water becomes at a higher and higher premium in the world? And this is the country in the world that has so much of that water. Are they going to be like Iraq, or are they going to be like Saudi Arabia in the next couple of years? You guys are like, what the hell are you talking about? Think about it. If they have the resource that's most coveted in the world, so right now the resource that's most coveted in the world is oil, and that's led to countries that have either very, very controlling political regimes or political regimes that are controlled by forces outside of that country. That's what I meant by Saudi Arabia and Iraq. And what that leads to is a very different look in Canada in the future. So we'll see. And over here we have the ice sheet that I was talking about earlier. This is Italy right here, right? So North Africa is down. No, it's further down. North Africa is down here. That was when North Africa was a much wetter place in the Pleistocene. When basically all of the Scandinavian shield was covered. A whole lot of the UK. Look, there's Ireland, and all the way down through Germany and into this is Poland and Czech Republic today. Okay. This is a moraine I'm going to talk about in just a minute, but but when we look at like the retreating of a glacier, so here's a glacier, and then that glacier is eventually gone. Look at the landscape that it leaves. We're going to talk about moraines in just a minute. This is the depositional landform that's created by glaciers. It can leave a glacial valley. It can leave like a river, possibly a lake. And these are the Kettle Lakes. And if you are from Oakland or have been to Oakland, the Kettle Lakes were created by glaciers. See? Once upon a time there was a glacier, carved out the landscape, left some little lakes, and now Oakland gets to have those lakes. Okay, periglacier or periglacial, that's an environment that's located in a very cold climate or near the margins of an alpine glacier. Okay, so basically our glaciers are going to be in two places, either in the very high latitudes or in the very low latitudes of Antarctica. So here's the Arctic Circle right here. um, and this is northern, no wait, sorry, this is northern Canada, and this is like Russia. So our periglacial environment, the kind of environment where we're going to see glaciers, is going to either be high up in latitude or high up in elevation. Now, I showed you a video earlier in the semester about Mount Everest, and I'm going to repost that so you can remind yourself of how elevation has a, makes a really big difference in temperature. But depending on how close you are to the equator, you have to go higher and higher up to get to an elevation where you're going to see a snow line. So if you're at a high latitude and a high elevation, um, or sorry, if you're at a high latitude, you're not going to have to go very far up in elevation before you get to the snow line. But if we're on the equator, we're going to have to go super, super high, something like 5 miles before we start to see this, what's called the snow line. So our periglacial, where glaciers are going to form, that's either going to be high up in latitude or high up in elevation, and that's the alpine reference right there. And then permafrost, that's where you essentially have, that's when we talk about tundra. Like this is tundra up here. That's where you have only certain types of plants that can live, that have adapted, certain animals that have adapted to that permafrost. You have soil, regolith, and bedrock that are going to be at a very, very cold temperature most of the year, and that's where we're going to see our glaciers. So what types of glaciers do we have? Well, we have alpine glaciers. Remember we talked about back up here. Our ice shelf or ice sheet. We talked about our ice cap, our ice field. So let's look at some alpine glaciers. That's high elevation glaciers. These guys, or we don't need to be gender specific, these y'alls are the kinds of glaciers that we're going to get at high latitude. And some of these, like this guy right here, this Tidewater Glacier, we could get at high latitude or at high elevation. So some glaciers will happen both at high latitude and high elevation, and some are exclusive to high elevation, and some are exclusive to high latitude. So let's look at our high latitude ones, and I'll tell you the ones that are exclusive to high latitude as we look at those. Oh, oh. Okay, so our alpine glaciers, those are glaciers that form at a high elevation. Typically, they flow down a steep mountain or slope and they fill up the valley below with water. So you get these alpine lakes that tend to be next to or close to an alpine glacier. And remember, I said that some glaciers you're going to see both at high elevation and high altitude. That's the same thing, high elevation and high latitude. And this Tidewater Glacier, you can either see, so this is a glacier that's coming down a mountain and it's emptying into a lake. So this is, I believe this is in Alaska right here, which is high latitude, but this could also happen at a high elevation. A cirque glacier, let's look, I have these in bigger. So a cirque glacier, that's going to occupy a steep bowl, a depression, right, in a mountain. And as it retreats, it's going to fill the valley below. So you get these nice, look at those nice alpine lakes. Actually, I can't tell if that's an alpine lake or if that's more of a glacier or just some snow. Well, here, glacial alpine lake. Tidewater, like I said, is a glacier that ends in a valley. It's filled by so you have like a glacier that's going to go all the way up this mountain, and then it's going to make its way down here. It's going to empty into a nice it's going to empty into a valley, but the big difference between like maybe a cirque or a tidewater is that it often empties into the sea. So it could start at a high elevation and then come the valley has some sort of an outlet or an inlet to the sea. It's very bulky. It rests at the valley floor. I've been right up to the end of a tidewater glacier, and they are massive. And this is where we're going to see icebergs. So icebergs are produced. The icebergs, that like took down the Titanic, for example, that is going to come off of a tidewater glacier. That's a glacier that ends in a valley that is the part of part of a sea. So you could have. It would be good if I had a map here. Let's go back to Alaska. There we go. So we're going to see tidewater glaciers in here. And what I mean by it can be a freshwater lake or it can be the sea is you could have a tidewater glacier that is mostly freshwater. So like this could be far enough away from the sea that it's freshwater, but it's going to eventually connect to seawater. So you're going to get brackish water in here, brackish water, that's just a little bit salty, and then it's going to make its way out to the sea. So I hope that made sense. Our valley glacier, that's going to flow down the steep sides of valleys, and you're going to have like you could have braided streams with a valley glacier. Uh, um, it's going to be in a valley, so it's going to be in a place without a whole lot of changing elevation, unlike the tidewater or the cirque. And then a Piedmont. Ooh, a Piedmont. This is the sign of a Piedmont right here. It's kind of like big elephant foot. Look at that. That's just amazing. So a Piedmont is a mountain glacier that flows out of the mountains and continues on to the surrounding lowland. Usually it's fed by a larger ice cap up here. And I had a picture of that way back here. Dun, 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 dun. Ah, there we go. Yeah. So we have our outlet glacier coming out, our Piedmont glacier. And then we have the ice cap. That's the dome, right? The glacier that like forms in over a dome, kind of like all rounded and spread out. So often our Piedmont glaciers are connected to this ice cap and flow down to a lower elevation and then fill a valley below. So we're looking at this rounded, connected glacier on the dome of a mountain, and then an arm of it is making its way down and filling a valley below. So that is our Piedmont glacier. Cirque Glacier, Valley Glacier, Piedmont Glacier. So there's a nice, let's see how it's looks like an elephant foot. There's another one. Once again, you've got the nice the larger dome of the ice cap, larger dome of the ice cap, larger dome of the ice cap, and then the glacier makes its way down and into the valley. So pretty. So how does a glacier form? Well, we've got the firn. Like I said, the firn is that loose surface snow. It's compact, it can be granular. We have a zone of accumulation. That's where the glacier is accumulating, where it's basically building. It's collecting more snow and more ice than is melting. The zone of ablation is where it's losing more ice than it's collecting. So this is basically where it's collecting, just like when we looked at the sand dunes and we had the windward side, and that's where the sand dune was building. We had the leeward side where it was kind of like the steep side that wasn't building up the sand dune. So our zone of accumulation, that's the part of the glacier that is building, that is accumulating, and the zone of ablation is the part of the glacier that is losing. It's losing its ice, it's melting. And there's going to be an equilibrium line somewhere between the zone of accumulation and somewhere between the zone of ablation. You have a line where nothing's really happening. It's neither building up or running off. Running off? Zone of accumulation, once again, that's where we're gaining ice. We see a net gain of ice. Our zone of ablation, that's where we see a net loss of ice. We are losing ice. The Fern limit, the equilibrium line, where basically nothing's happening. We are both, we are neither gaining or losing. And then a moraine. Ooh, we're going to get to moraines in just a minute. But a moraine is a landform. It's a depositional landform that is created from a glacier. So remember I said that a glacier in itself is a landform because it's frozen ice, but it's also creating both erosional landforms and depositional landforms. Calving, that's when you see the breaking off of a glacier, like a tidewater glacier. Tidewater glaciers that lead to icebergs. The breaking off of that iceberg is called calving. So the breaking off of that iceberg is called calving. And there is calving. There's it. It's going to break off. It's going to go float and be an iceberg. Ooh, there it is again. It's going to go float and be an iceberg, but the process of this is called calving. You can really see that blue ice that I was talking about. That's the ice you don't want to touch. It'll burn you. It's really, really cold. So let's look at some of the landforms that are created from glaciers. We've looked at glaciers. We've looked at why glaciers are important. We're going to start with our erosional landforms. So an erosional landform, that's when material is taken away in order to create a landform. And a fjord, we talked about when we talked about rivers, if you remember. But a fjord is a glacial valley that is filled with seawater, and it's an outlet to the sea. So this would be a fjord. See how it kind of looks like a river, but essentially it was made by a glacier. A glacier would have carved this nice giant U-shaped valley and then filled it with nice fresh water. And that fresh water eventually makes its way out into the open sea. And if you remember when we talked about this with rivers, there isn't like a delta. There's no like depositional landform in between the fjord as it makes its way out to the sea. It's just like you could be floating along in here and then suddenly you just see the open sea in front of you and you haven't really noticed a difference in water, basically. Like you never got to the end of the river. The river doesn't really end. It just like marries itself to the water. Why was marry the only word that I could think of? Okay, so a glacier, as we know, is very, very heavy. It presses down, it compresses the crust, it compresses the earth right here. It's not necessarily the crust, but it compresses the earth and it carves out the earth. And so when that glacier goes away, when it melts or when it retreats, you now have this nice, deep, U-shaped valley. The difference with a fjord and just a glacial valley is that this fjord is going to go out to the sea. It's going to have an outlet to the ocean. You see a whole lot in Norway. I say unsurprisingly here, maybe because of the name fjord, but it's also should be not a big surprise to you that Norway has a whole lot of fjords or landscapes that are carved by ice, because Norway is high up in latitude. It has a whole lot of mountains. It's a very mountainous country. You got gnomes walking around and elves walking around there. They are not creatures that like the heat. So it shouldn't surprise you. But if it does, congratulations. I didn't think I could still surprise you. Here is a glacial fjord. See what I'm talking about? Like, can't you see some elves just wandering down here? You've got a waterfall. I mean, geez, Norway is a beautiful country. A U-shaped valley, literally like U-shaped valley that can be carved out by a glacier, as opposed to the V-shaped valley that's created from rivers. See that sharp V? And we've got a nice like broad U here. This is near Mount Hood in Oregon. Juneau, and that's the capital of Alaska. I got married here one time number 3, on a glacier way back in here. What was the name of that glacier? Oh yeah, Mendenhall Glacier. So Juneau is the capital of Alaska, and it's a pretty significant city for Alaska. Um, and you've got this, it's basically built in a glacial valley. So you have this glacial valley, part of it is filled with water, and that water is going to make its way out into open ocean eventually. Um, and you have this flat part of it in the valley that's not covered in water, and it kind of like snakes back in here, and then there's a whole city back here. But so this is a nice valley that's created from a glacier, and you have a little bit of flowing water, and you have a little bit of land, you have a little bit of a capital. Sometimes you might notice like big rocks in the middle of a valley. Lee Vining, for example, in the Sierra Nevada, or here in Yosemite, once again in the Sierra Nevada, and you might think, how did that get there? Well, it might have been moved. This definitely was moved by a glacier. Glaciers are, like I said, gigantic frozen rivers, so they have the power not just to carve out a U-shaped valley like this, but they also have the power to move and just kind of abandon rocks in the middle of nowhere. Once again, Finland. There we go. Why am I showing you this again? Just so you see it again, I guess. You've got, once again, the zone of accumulation where we have a net gain, the zone of ablation where we have a net loss, and then we're going to have the landforms, the depositional landforms that form around a glacier. So we looked at the erosional landforms, the U-shaped valley, the fjord, and then let's look at some depositional. So our depositional landforms that are created by, and remember, that's deposited material, material that's been eroded and moved and now deposited. So our depositional landforms around a glacier, they're called moraines, a moraine. So you're going to have moraines at the end, at the terminus, right? The terminal moraine right here. And I showed you a picture of that when we looked back here at Oakland. Oakland, where are you? So this was a terminal moraine. See how that's like now going to be a little hill? People don't even know that they're walking on a terminal moraine when they're in Oakland. Ah! Oh, man. Now I have to do that all over again. But you guys are probably excited because it means we are close to the end. Dun, 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 dun. How are you guys doing? Like you can answer. Okay. Dun, 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 dun. All right. So our terminal moraine, that's our landform that's going to be created from all the material that's been moved, eroded, and transported by this glacier. And then our lateral moraine is going to be along the side. So lateral moraine, so remember moraine is the term for the depositional landforms that are created from glaciers. And the one that's running along the side is the lateral. And the one that's going to be at the end is the terminal, at the terminus. And then you can also have medial moraines right in the middle. So if we have, this is a valley glacier, valley glaciers can have streams braiding through them. They can also have these medial moraines. So a moraine that's kind of running along the middle. This is either a medial or no, this looks like a, what's that look like? It's probably, oh, it looks like a lateral moraine. It's probably a lateral moraine running along the side. And there you got the nice lateral moraines. Down here you're going to have a terminal moraine. And that's it. I hope you all enjoyed this, our view of glaciers and sand dunes. I hope that you are all well. Please don't hesitate to schedule office hours with me. We can do FaceTime, we can email, whatever, but I'm happy to talk to you all. I hope that you're doing well. Don't forget you have a quiz. It started about an hour ago, so have fun with that. Good luck on that. All right, bye. I'll see you when we talk about soils. Oh, yay, soils.